The ideas expressed in the following presentations are those of the speakers and do not necessarily reflect the views of ACI or its committees. ACI web sessions are recorded at ACI conventions or other concrete industry events and will be made available for viewing free of charge for 1 week. Thereafter, they will be archived on the ACI website or added to ACI's online CEU program, depending on their content.
Good morning, everyone. First of all, I want to thank you all for giving us the opportunity to present our work here. This work has been done as part of my PhD study at University of Miami, and it's a joint work with Mr. Doug Rummel at Hughes Brother Incorporation and Dr. John Mayers at University of Missouri University of Science and Technology and Dr. Antonio Nanni from University of Miami. My presentation is on long-term durability of GFRP internal reinforcement in concrete structures. In this presentation, I will briefly talk about the general ideas of GFRP and the approach of durability study that we are taking in this specific study. I will talk briefly about the field structures that we chose as our case studies, the sample extraction preparation, and also the concrete and GFRP characterization, which is the main focus of our study. And at the end, I will finish with some conclusive remarks. As you may know, GFRP stands for glass fiber reinforced polymers. And GFRP bars are made of glass fibers as the load-carrying members and resin, which protects the fiber and transfers the load among them. We all know that steel rebars are still the main and traditional reinforcement for concrete, but the steel suffers from the corrosion problem. The corrosion of black steel lowers the service life of the structure and eventually leads to repair and maintenance costs and in some cases even safety issues. On the other hand, GFRP bars are emerging as an effective solution for resolving this problem, especially for the structures which are exposed to aggressive environments such as bridges or seawalls, marine structures, and they are offering several advantages. The most important for us is corrosion-resistant properties because it's a composite material. High strength-to-weight ratio, which is generally 4 times lighter than steel. Magnetic transparency, which makes it an ideal case for, let's say, construction in MRI units at hospitals, and also in some cases ease of demolishing in some temporary applications. One thing that is going to help GFRP technology to get widespread applications, especially in construction and infrastructures, is providing more and more proof of its long-term durability. Because for any composite material in any application, long-term durability is a big concern. So this is the same in this case. Usually the approach that has been taken in the literature for approving the durability is trying to provide, or let's say simulating, the concrete atmosphere. So usually the solutions with high alkalinity and sometimes even elevated temperatures are provided for the GFRPs to be exposed to, and then the residual mechanical properties are studied. But the approach that we are taking in this study is using the real samples from the real field structures and extracting them after years of service and investigating them to show that what has happened to them after, let's say, a decade of service or 20 years of service. And we believe that that is a real indication whether it has a long-term durability or not, and let's say what happened to them after 15 years. And as you may imagine, because of the difficulty of this type of project, let's say for the coordination for sample extraction, for the ownership problems and the safety issues, the traffic control, there are only a few types of studies. And the purpose of this specific study is to contribute more to this part of the literature. So for our study, 2 bridges, both in the city of Rolla, Missouri, has been chosen. One of them, which from the rest of the presentation I will refer it to Vodka. Vodka Bridge is a box culvert bridge built in 1999. And the other one, which I will refer to as a Southview Bridge, again is in the same geographical location, and it has been built in 2004, and both of them incorporated GFRP as part of the construction. I will talk shortly about these two structures. The Vodka Bridge was built in 1999 in the city of Roland, Missouri, to replace the old bridge. Here you can see the old bridge, which was made of concrete and 3 encased steel pipes, and it was unsafe to operate because of the extensive corrosion of the steel pipes and also cracking in the concrete. The new bridge is made of 18 boxes in 2 rows of 9. The boxes are 1.5 by 1.5 meter and the thickness of 150 millimeter. And the total length of the bridge is 11 meter. The reinforced concrete boxes were made of concrete and the entirely numbered 2 GFRP bars. As you can see here in the picture at the right, there is a GFRP cage completely made of number 2 GFRP bars, and that is basically the only reinforcement for these boxes. In order to share with you what was the exposure of this bridge regarding the environmental situation, the bridge was exposed to thermal range of -6 to +32 degrees of centigrade, wet and dry cycles, freeze-thaw cycles, and also exposure to de-icing salts. So fairly, it has been exposed to different types of extreme situations, and it can provide us a good case study. The next bridge, which I call it Southview Bridge, has been originally has been built with 4 steel reinforced concrete box culverts, but the bridge went through an expansion in 2004 with the addition of 1 additional lane and a sidewalk. And number 3, 4, and 6 GFRP bars has been used, and also number 3 prestressed carbon FRP tendons in the construction of this bridge. In 2016, expert personnel extracted several concrete cores from these 2 structures at different locations. The structures were taken from the bottom surface of the GFRP box culverts, which logically has been exposed to more moisture, and also from the bridge deck of the Southview Bridge. After the samples has been shipped to the University of Miami lab, we started working on the samples and trying to extract the GFRP bars, and as these bars are really valuable for us and we didn't want to lose any part of it, so it takes lots of patience to remove all the pieces of GFRP in those cores. After the GFRP were taken out from the cores, before characterizing the GFRP itself, first we provide a general characterization of the concrete itself to show that what has happened to concrete after 12 and 17 years of service for these 2 bridges. So first, the pH of the concrete was found to be in the range of 11 to 12, which is an expected range for the type of the concrete and the age of the concrete. And also we performed the chloride diffusion test and carbonation depths, and we found that there was no carbonation in the concrete cores and also no sign of chloride diffusion. So while having no carbonation could be really an ideal case for steel rebars because it postpones the corrosion, but completely different, it's a really worse situation for the GFRP bars, because whatever the alkalinity of the concrete core is higher and there is no carbonation, it provides a more severe case for the GFRP, because GFRPs theoretically are supposed to be weak in alkaline solutions, alkaline environments. So from now, the main focus of our study started, which is the characterization of the GFRP itself. Different mechanical tests and microscopic examination has been performed on the extracted samples, which included the SCM analysis, EDS, horizontal shear test, glass transition temperature, and also fiber content. And I will go through each of them one by one. So a scanning electron microscopy was performed, and the main purpose for that was to provide into even a single fiber level to see that what has happened to the microstructure of these composite materials. As you can see here in this picture, this is the SCM in 2 different magnification levels, and I need to say that we have performed the SCM for several samples and for several locations, random locations, and here I'm presenting only representative samples. So the picture at the left is in the magnification level of 200, and the one at the right is at 800 magnification. And as you can see here, and also in the next page, which is the same situation, but a slightly higher magnification for the Southview Bridge, which are the left one, the 500 magnification and 1400 magnification. So basically, if you see this photo, which is taken out after 17 years of service, and this one, after 12 years of service, basically nothing has happened to the microstructure of these GFRP bars. I think this is really one of the strongest evidence that we can provide that these materials are durable, and in a real field application, they can be a proper solution for corrosion of the black steel rebars. So as I mentioned, no apparent sign of deterioration in the fibers, matrix, and also fiber-matrix interface was observed. Glass fibers appear to be intact with no loss of cross-sectional areas, as you can see in those two pictures. And we take it one step further. We performed the Eds analysis, and the purpose for Eds analysis was to provide the existing chemical elements in these materials to see whether there was any sign of attack of any chemical or alkaline elements. And again, we saw no sign of chemical attack. The fibers, the elements that we found in these two samples, these two representative samples, were the element that we generally expect from GFRP samples, right? So there were silicon, aluminum, and calcium mainly, which are the main components of the glass fiber, and also carbon and, of course, the oxygen for the resin itself. And it was the same situation for both bridges. From now, our tests are mainly the mechanical point of view and not the microstructure anymore. One of the most interesting one for us was the horizontal shear strength. This plays a really important role as an indication of durability, because horizontal shear, as you can imagine, deals with the mechanical properties at the interface of fibers and resin. And any kind of degradation, we can see a proper site at the interface. And then the loss of bond between the fibers and resin, and eventually losing the load-carrying properties. So horizontal shear strength was really important for us, but unfortunately for this specific bridge, there was no historical data for the exact GFRP bars used in the construction, so to be able to compare that. So what we did was we performed the same test with the same setup on the samples produced by the same manufacturer in 2015, and use them as a benchmark of comparison. Because generally we expect the technology to become better and better during years. So with this type of comparison, this is even a more conservative type of comparison, because we expect that it has been improved. So the test has been performed following the ASTM standard D4475. And the test was performed only on the samples from the Southview Bridge, because the test stage was not available to perform the test for the samples taken out from the Vodka Bridge, because they had a really small diameter. So in the samples performed for this bridge, really interestingly, the result was 5% higher than the average results we performed on the control samples. So again, I need to mention that maybe this 5% increase is not a real increase, because we are not comparing the apple to apple exactly. But the least thing we can say is that for sure there was no degradation, and the property was in the same range. The next test we performed was dynamic mechanical analysis, DMA, to investigate the glass transition temperature. That parameter is also really critical for us, because this is the temperature which, beyond that temperature, GFRP bars loses their ability to transfer the load dramatically, because the state of the resin changes from solid to liquid type of stage. So the dynamic mechanical analysis was performed following the ASTM E1640. And again, the result, the same as the shear test, was compared to the samples produced from the same manufacturer but produced in 2015. And again, what we found that approximately 25% of increase in the transition glass temperature during the years. And we saw the same type of result for different studies that we performed. And the reason we believe that this increase can happen is the additional curing of the resin over time with the exposure to sun and cross-linking the polymer. So again, this is another sign that this critical parameter of GFRP bars has not been degraded at all after 17 and 12 years of service. And finally, the fiber content. The fiber content was performed following the ASTM D2584, and the results again were compared with the test produced in 2015. The measured fiber content, as you can imagine, was exactly in the expected range and still well beyond the minimum requirement of 70% by mass. So the results were 82 and 73%, which are in the exact range that we expect to see the fiber content ratio. So as a conclusion, as I mentioned, GFRP and concrete samples were extracted from 2 bridges, both of them more than a decade old. First, the concrete was tested, and the pH was in the expected range. The no carbonation and chloride diffusion was observed in the concrete. And next, different mechanical tests and microscopy examination was performed to provide the evidence of the durability of this material. So microscopy examination did not show any sign of GFRP degradation nor any sign of chemical attacks to these materials. And in sense of mechanical properties, the horizontal shear strengths showed 5% of increase compared to the benchmark values, and the same case for the glass transition temperature, and also the fiber content was in the exact expected range. So the main message of our study is GFRP is a durable material, and this study shows that after years of service, basically nothing has happened to this material, and specifically for structures which are exposed to aggressive environment, as I mentioned, such as marine structures, bridges, seawalls. This could be a perfect and effective solution for removing the corrosion problem of the steel rebars. Thank you very much for your attention. If you have any question, I will be happy to answer.
Do you have any questions?
Okay.
I do have one
Sure.
question, and that was just with regard to the
Yes.
microscope pictures. I noticed there were lots of white spots on those
Yeah,
pictures. So, and maybe guess, oh, that might have been deterioration. But what was that?
Because I was also suspicious about them, but I compared them with them because first of all, like sample preparation for this type of materials, because it has been made of 2 components which has a completely different hardness, the resin and the fibers, is a really sensitive procedure. And with a slight change of sample preparation, the sample can be not good for SCM observation. So, and in any human sample preparation, there is a consistency, right? So in order to be consistent, I performed the same procedure on controlled samples, and I, like pristine samples, right? No deterioration, nothing. And those spot dots were also still there because, and in the EDS we don't see that there are like chemical changes. So mainly they are like the roughness of the part of the roughness of the surface, which and you can see that. Let me show you here in this image. So I have done a better work in polishing probably, and in this one it was slightly more spots, and also some residues that stays there after, like during the cleaning, and those and this one actually it's the perfect evidence that there are not any additional like elements or chemical attacks. Yeah.
Do you have any information about the concrete mix that they used in those bridges, and is that information published? And the other thing is, I'm really not sure if the argument that there was a 5% increase in the shear strength is really valid. We don't know what the original material was, and I'm wondering if there was degradation. Is any of the other tests that you have done can say that we don't have any indication that the shear strength would have suffered?
I completely agree with you. As I mentioned, the perfect situation would be having the exact samples, and we had the same situation for a different bridge in Texas. And we compared the shear test with the same shear test data which has been performed in 15 years ago, right? And those are the perfect evidence. But still, another argument is these tests, we cannot perform these tests in a lot, like several repetition of samples, because we cannot core more than a certain amount of samples, definitely, right? So at the end, there would be a limited samples, and especially in a shear, transfer shear test, lot by lot and production lot by production lot, slightly there is a variation by even by 10%, 15%. So this is part of like the general, let's say, a statistical evaluation error. And even if we have the historical data from the exact GFRP bars used in that bridge, but we are not sure that is the same bar or not that we are taking out. So again, we may see a slightly difference, a slightly increase. I agree with you that there may not be an exact increase of 5%, but at least we were happy that it is not showing us that there were a dramatic or even significant reduction of strengths. And the same, to answer your other question, yeah, the same situation we saw in the other tests that we performed.
Now, please join me in